Welcome to the second class of this course. So in this class I will be solving very simple first order and second order differential equations. The motivation behind it is basically to let you know that how simple the method is. Okay, in the next class I will try to formalize things like when at all we can find a solution, a series solution. So there will be ordinary points, singular points, different kind of singular points, regular singular points, essential singular points. So those things I will formally define in the next class. Okay, so in this class I will take very simple examples and try to find series solutions. So let's start. So at the beginning, let me write a statement. Let's say there is a polynomial. Let's say x equals to a0 plus a1 x plus a2 x square plus a3 x cube plus dot 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 plus an x to the power n. Okay, so nth order polynomial, and where x is the variable and ai's are constant. In that case, if fx equals to 0, or rather a0 plus a1x plus a2 x square plus a3 x cube plus dot 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 plus an x to the power n, if it equals to 0, in that case we can say all the ai's are individually 0. So all ai's for I equals to 0, 1, 2, dot 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 n, all the ai's are individually 0. Okay, so all these coefficients, these are 0. The proof is very simple. You can pause the video and try to think for a moment how to prove it. It's very simple. So first we will show that an is 0. How to show that? If you do nth order derivative of fx, we already know that fx equals to 0. Then if you do the nth order derivative of fx, dxn, then what you will get? You will get n times n minus 1 dot 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 2 times 1 times an equals to 0, and this cannot be 0. It means an equals to 0, right? So then as an equals to 0, then what we have? So we are left with a0 plus a1x plus a2 x cube plus dot 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 a n minus 1 x to the power n minus 1 equals to 0. That's what we are left with. So now this is our new, let's say, fx, or rather call it f1x. Now again you will take n minus 1th derivative, so ddx n minus 1. f1x. In that case, what you will get? You will get some n dependent factors like n minus 1, n minus 2, dot 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 2 times 1, and what you will get? Times n minus 1 equals to 0. So then this cannot be 0. It means a n minus 1 equals to 0. Okay. So now what you are left with? So you already proved that a n minus 1 equals to 0. So then you are left with, let's say, f2x, which is a0 plus a1x plus dot 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 plus a n minus 2 x to the power n minus 2. So n minus 2 equals to 0. Okay. And then again you will take the derivative like n minus 2 2th order derivative, and you will show that okay, n minus 2 equals to 0. So in that way, so you can just go down and just say just show that all the ai's are 0. So it's a very easy proof. Okay. So the statement is, if a0 plus a1x plus a2x square plus a3x cube dot 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 an x to or n equals to 0, then all these coefficients, these are individually 0. Why this is useful? So in this course, so while solving this, while getting the series solution of the differential equations, we need to compare the coefficients basically. So you will get like, there will be like a n x to the power n, and here in the left hand side you will find something like that, and let's say in the right hand side you are finding that cn x to the power n, for example, or let's say cn x to the power n minus 1, for example. So okay, these kind of summations you have. So in that case, what you can do is basically you can compare the nth power, like this, compare the coefficients of same power of x. So in that case, if I compare it, so then what we will get is basically a n, a n equals to, so I can also write it as sum over of, if I, in the summation, if I write x to the power n, so in that case it will be cn plus 1, right? So in that case a n will be equals to cn plus 1. So I can compare the coefficients using this theorem. So that's the importance of the theory. Okay. So now let me start with some very simple examples. Okay. So first I will try to find out series solution of some very simple first order differential equations. So let's take example 1. Let's take a very simple first order differential equation, that is dy dx equals to y. So we all know what the solution is. So we can write it as dy by y equals to dx, and I can do the integration with some integration constant, let's say c. In that case it will be ln y equals to x plus c plus y equals to some constant, let's say a times e to the power x, okay, where a will be in this case e to the power c. So you already know that this will be the solution. So this is the analytic solution of this differential equation. So let's find a series solution. Okay. So let's assume y equals to, so we'll assume that y is a power series in x. So a n x to the power n equals to 0 to infinity. Okay. So in that case, okay, so it's a power series around x equals to 0. So we are trying to find out the solution in the neighborhood of x equals to 0. So then we will calculate the dy dx. Okay, dy dx equals to sum over of n equals to 0 to infinity a n d dx of x to the power n equals to sum over of n equals to 0 to infinity n a n x to the power n minus 1. Okay, and now if you put this dy dx and y in this differential equation, what you will get? You will get, okay, before doing that, let me do something else. Okay, so this power series, so it has a x, so here x has a power of n minus 1. So I want to do some comparison of powers. So in that case, for this series, this dy dx, this series, I want to write it as a series where it will be x to the power n, not n minus 1. So how to do that? It's just the index shifting. So we will take another index m, which is m minus n minus 1. Okay, so when n equals to 0, or let me write another step here. So if you put n equals to 0, then this term is 0, so I can write it as this equals to n, let's put n equals to 0. So if I put n equals to 0, so then there is n, so this term will be 0. So there will be 0 plus n equals to 1 to infinity n a n x to the power n minus 1. So n equals to 0 term, that is 0, so I am excluding it from the summation. Okay, so now what I have is basically dy dx equals to n equals to 1 to infinity n a n x to the power n minus 1. Very simple. So now let's define a variable which is m equals to n minus 1, right? And if so, here n is starting from 1. So if n equals to 1, so if n equals to 1, what will be m? M will be, so if n equals to 1, m will be 0. So n equals to 0. And if n tends to infinity, this is m also tends to infinity, right? So I can just and also n equals to m plus 1. So I can just replace this n with m, because it was starting with n equals to 1. Now it will start with m equals to 0, because n equals to 1 means m equals to 0. So m equals to 0 to infinity, and in place of n I will write m plus 1, m plus 1, a m plus 1, x to the power m. Okay, and as it's a summation, summation m is a summation index, so in that case I can replace m by n. Sorry, an plus 1 dy dx. Very simple. So now we will use this dy dx and this y in this differential equation. So what we have is basically dy dx equals to y, right? So now we will write the series instead of dy dx, it is n plus 1 times an plus 1 x to the power n, and y is n equals to 0 to infinity an x to the power n. I can compare the nth power from right hand and left hand side. Also I can do something else, n equals to 0 to infinity. I can take this term to the left hand side. That's what I will do. From this step also I can compare the coefficients basically. N plus 1 an plus 1 minus an times x to the power n equals to 0, and now using this statement that if this power series equals to 0, so in that case every coefficient will be 0. That's the application of the statement, this theorem. Okay, so what I will write is n plus 1 an plus 1 minus an equals to 0, implies an plus 1 equals to an divided by n plus 1. This equation, this kind of equations, these are called the recurrence relation. What does it mean? So it says that if we know an, we can find an plus 1. So it's kind of a recursive method. It gives a recursive way to find the next element if we know the previous elements. So that's why it is called the recurrence relation. So let's see how this kind of recurrence relation will be helpful to get a power series solution. So let's start with 0, n equals to 0, that is a0. So we don't know what is a0. So let's assume that okay, we have a constant that is a0. Series starts at n equals to 0. So then in this recurrence relation, let's put n equals to 0. So let's put n equals to 0 in this recurrence relation. So what we will get? We will get, if you put n equals to 0, then you will get a1 equals to a0 divided by 1, or rather a1 equals to a0. Okay, if we put n equals to 1 in this recurrence relation, then what you will get? You will get a2 equals to 1 plus 1 2 equals to a1 divided by 2, right? And what is a1? A1 is a0 by 1, so it is a0 by 2 times 1, which is a0 by 2 factorial. Okay, this is a0, right? Now let's say put n equals to 2 in the recurrence relation. So if I put n equals to 2, I will get a3 equals to a2 by 3, right? So a3 equals to a2 by 3 equals to a2 is, we know that a0 by 2 factorial, so it is a0 by 3 dot 2 factorial, which is nothing but 3 factorial. So dot 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 we can write that an will be a0 by n factorial, following this pattern. So in that case the series will be, y will be, so what we assumed, y will be an x to the power n equals to 0 to infinity, right? And if I put the value of n's, so it will be x to the power n equals to 0 to infinity equals to, I can take a0 outside, n equals to 0 to infinity x to the power n divided by n factorial. So this is the series solution. X to the power n divided by n factorial, n equals to 0 to infinity. So this is the series solution of this differential equation. No, x to the power n around x equals to 0. So the power series we have assumed here. So in general the power series notation was an x to the x minus x naught to the power n, okay, sum over n. Here x0 I have assumed 0. So this is, here I was trying to find out a solution in the neighborhood of 0, x equals to 0, okay, and we got this solution. Now what was the analytical solution? We know that it was some constant multiplies with e to the power x, and you can see what we are getting here. This is basically the series expansion of e to the power x, no? Taylor series expansion of e to the power x at x equals to 0. So the solution we are getting is, I mean, very much understandable, no? This is where we are expecting to get. And the interesting thing is basically, though we are finding a solution around x equals to 0, but this solution will be valid for all the x. It's because the series is convergent. So it has we have already proved in the last class that this series, it has a radius of convergence which tends to infinity. So though we are finding a solution in the neighborhood of x equals to 0, the radius of convergence of the series is infinity. That means it will be valid for all x. Let's take another example. So it's very simple. But these are very simple examples also. Okay. The second example is dy dx equals to 3x square times y. It's a bit complicated, but okay, we can already find, or we already know how to find out the analytical solution. That is, write dy by y equals to 3x square dx and do the integration. There will be an integration constant c. So what we will get, it's ln y equals to x cube plus c, or y equals to some a times e to the power x cube. This is the analytical solution. Now let's try to find out a series solution in the neighborhood of x equals to 0. So let's assume y equals to sum over a n x to the power n equals to 0 to infinity. Okay, we have assumed the solution. Now what our job is to find these coefficients, same as what we did in the last example. So okay, so let's calculate dy dx. So dy dx equals to sum over n equals to 0 to infinity n a n x to the power n minus 1, right, which equals to, so n equals to 1 to infinity n a n x to the power n minus 1. It's because n equals to 0th term is 0. If we put n equals to 0, then because here is n sitting, it will be 0. So I can start the index from n equals to 1 safely. Now again we will do the coefficient transfer. So that is, we already did it here, so I will not do that again. So it will be n minus 1 times n plus 1 times n plus 1 x to the power n. Okay, so it is n equals to 0 to infinity n plus 1 n plus 1 x to the power n. You need to do the index shift. It's same as what we did in the last example. Here if you follow these steps, you will get the same expression. Now another, in the right hand side, what we have is 3x square y. The RHS we have is 3x square y, which is 3 times sum over n equals to 0 to infinity a n x to the power n plus 2. Okay, so yeah, so here again x has a power of n plus 2, right, and we want to compare the powers. So that means we want to write this series as some coefficient x to the power n in this way. Okay, you can just pause the video and try to do it yourself. I mean, we will assume m equals to n plus 2 here. So as it is n plus 2, so I will assume that m equals to n plus 2. now implies n equals to m minus 2. Okay, now if n equals to 0, then m equals to 2, and if n equals to n tends to infinity, then m also tends to infinity. So in that case, I can replace this summation with m index. Replace this n index with m index. So n equals to 0, it means m equals to 2 to infinity. A m minus 2 x to the power m. And as m is a summation index, I can write it as n equals to 2 to infinity a n minus 2 x to the power n. It just replace m by n, but this n is not same as this n. So it's a different summation index I am using. Okay. So now we can safely compare the index or the coefficients. The equation we have is basically dy dx equals to 3x square y, and if we replace it with the series we have, then it will be n equals to 0 to infinity n plus 1 times a n plus 1, this expression n plus 1 times a n plus 1 x to the power n equals to 3 times sum over n equals to 2 to infinity a n minus 2 x to the power n. So we got the equation. Now what to do? Can we compare the coefficients? Think about a bit. Can we now compare the coefficients? Like we have the same power of x, right? X to the both are x to the power n. So it seems like we can compare the coefficients. But wait, the summation here, it starts from n equals to 2, and here it starts from n equals to 0. What does it mean? It means in this summation, you will not get x to the power 0, you will not get x to the power 0, you will not get x to the power 1. But here you will get them, because here n is starting from n equals to 0. So what we need to do is basically so this was starting from n equals to 0. So what I will do is write n equals to 0th term, which is, so if n equals to 0 I put, so then it will be 1 multiplied with a1, so it is a1 x to the power 0, so that means it's just a1, x to the power 0 is 1, plus I will put n equals to 1 for the next term. So if I put n equals to 1, so then it's 2 times a2 times x, okay, and for other term I will write the summation n equals to 2 to infinity n plus 1 a n plus 1 x to the power n equals to 3 times sum over n equals to 2 to infinity a n minus 2 x to the power. So now what we can do is we can write a1 plus 2 a2x plus, I can take this to the left hand side, this term, so it will be then n equals to 2 to infinity. So both have the same, summation index, range of summation index. Like in both cases, n is now going from n equals to 2 to infinity. So now we can take them in a single bracket. N plus 1 minus 3 times n minus 2 x to the power n equals to 0. Okay, so here it starts with x to the power 2. It starts with x to the power 2. So here x to the power 0 and x to the power 1, these two terms. So using the statement or theorem I stated in the beginning, I can write a1 equals to 0, a2 equals to 0, and n plus 1 an plus 1 minus 3 times an minus 2 equals to 0. So this will give us the recurrence relation, which is an plus 1 equals to 3 divided by n plus 1 times a n minus 2 . So this is our recurrence relation. Good. So now, we have already know, we already know that this a00 is a1 equals to 0 and a2 equals to 0. Okay. Let's start with, we don't know what is a0. A0 is not 0. So let's start with a0. Let's assume a0 is a constant. So in that case, I will use this recurrence relation to get the other terms, So if I put n equals to 2 in this recurrence relation, put n equals to 2. In that case, what we will get? We will get a3 equals to 3 times 3 divided by 3 times a0, which equals to a0. If I put n equals to 3, what we will get? We will get, if I put 3, then we will get a 4 equals to 3 times 3 by 4 times a1, right? But a1 we know that a1 is 0, and we also know a2 is also 0. So that means a4 is also 0. Okay. Similarly, if I put n equals to 4, then we will get a5, which equals to some term into a2 equals to 0, because a2 is 0. Then if I put n equals to 5, we will get a6 equals to, okay, so this is the recurrence relation. So we will get a6 equals to 3 divided by 6 times a3, right, equals to 1 by 2. a3 equals to a0 by 2 factorial, right? a3 equals to a0 by 1. Similarly, now if I put n equals to 6, so then what we will get? a7, but it will be some factor times a4, and we know that a4 is equals to 0. That means this is 0. Similarly, if I put n equals to 7, we will get a8, which will be some factor times a5, and we know a5 equals to 0, that means a8 is also 0. So n equals to, if I put n equals to 8 in this recurrence relation, we will get a9 equals to, so now a9 equals to, we have put n equals to 8, that means in a9, if I put n equals to 8, then a9 equals to 3 by 9, you know, 3 by 9 times a6, n equals to 8 here, so 3 by 9 times a6, which is 1 by 3 times a6, and we know a6 is a0 by 2 factorial, so that means it will be a0 by 3 factorial. So what we have is only the, you know, a3i, these kind of terms will survive. Only the terms which whose indexes are in multiplication of 3, those are surviving. Okay, so this is surviving, and the other two, these are not surviving. Then again this is surviving, and the other two, these are not surviving, right? And then again this is surviving. So we can start with a0, and then only those terms which are in whose index are in multiplication of 3, then those will survive, and you know, their and their coefficients will be a0 I factorial. I can follow, so you can follow this pattern, right? Like here 3i, I equals to 1, so it is 1. Here for 3i 6, so it means I equals to 2, so it's 2 factorial. It's a9, it is a0 by 3 factorial, and here I equals to what? I equals to 3, that means it's 3 factorial. So what we have is basically y will be, the solution will be sum over of n equals to 0 to infinity a of 3n times x to the power 3n, or write it like that. I don't want to confuse at this moment, x to the power n. Okay, and what n is, basically n is 3i, so only the 3ith term will survive basically. So 3i equals to 0 to infinity a 3i 6 to the power 3i. Now 3i goes from 0 to infinity, means I also goes from 0 to infinity. So here I, sorry, it's not 3i, it's I. Only these term will survive. So in that case I can write also, I mean it's a summation index, so I can write n equals to 0 to infinity also. A of 3i x to the power, sorry, 3n x to the power 3n, right? So what we have is basically, and a of 3n we know that it is 0 by n factorial, a0 by n factorial, so which is sum over of n equals to 0 to infinity a0 by n factorial x to the power 3n is y. a3i we know that a0 by I factorial, so a3n will be a0 by n factorial. So I can write this a0 outside, and then what we have is basically our series solution, which is n equals to 0 to infinity x to the power 3n divided by n factorial. So this is our solution. And what we are expecting e to the power x cube, right? And if you look at the series, see, it is sum over of x cube to the power n divided by n factorial, n equals to 0 to infinity, which is nothing but series expansion of a to the power x cube. That's what we would expect. So things are making sense, and that was the motivation of choosing these simple examples and first solve a few. To let you know that these things are not out of the blue. Okay, let's take a few second order differential equations, second order ODEs. Okay, so second order ODEs. Let's take example 1. Okay, let's take a equation of simple harmonic motion, that is y d2y dt2 equals to minus omega square y, and we already know what will be the solution. The solution is y equals to some constant, let's say a, sine of omega t plus b cos of omega t. This is the analytic solution, we all know, right? Let's find out the series solution. Same method, you can just pause the video and try to do it yourself. Write y as a power series an x to the power n equals to 0 to infinity, and now find out y dot. Y dot means dy dt. Okay, so I will be using y dot to imply dy dt, or dot I am reserving it for the derivative with respect to time, and for all other variable I will write as dash y dash. It will be dy dx. So then y dot will be n equals to 0 to infinity n an x to the power n minus 1. Good. And again I can omit the 0th index, and I can start at n equals to 1 n x to the power n minus 1. If I take another derivative, then it will be n equals to 1 to infinity n minus 1 an x to the power n minus 2. And also if I put n equals to 1, then you see this term is 0 because of n minus 1, so the term will be 0. So I can start from n equals to 2, n equals to 2 to infinity n minus 1. Good. Now we want to compare the coefficients, so we don't want this x to the power n minus 2 kind of terms. Okay, we want x to the power n, right? So what we will do, we will do the index shift. So we will take m equals to n minus 2. Good. It implies n equals to m plus 2, and when n equals to 2, m equals to 0. So if n equals to 2, n equals to if n equals to 2, m equals to 0, and if n tends to infinity, m also tends to infinity, right? Then I can just replace the index n with m, so it will be m equals to 0 to infinity, m plus 2 times m plus 1 am plus 2 x to the power m. Sorry. Y is a function of time. Really sorry. So y is a function of time, right? So it's not a power series in x, it's a power series in time. It's t. Extremely sorry for that. Okay. T to the power m. So now we will just put this y double dot and this y in this differential equation. So then what we will get is basically y double dot equals to minus of omega square y, right? Which is nothing but, okay, instead of m equals to 0, I can write n. So it's a summation index. Okay, so I am writing it as n equals to 0 to infinity, n plus 2, n plus 1, an plus 2 t to the power n equals to minus omega square summation n equals to 0 to infinity an t to the power n. Now you can see that the summation index is both in both right hand side and left hand side, it is starting from n equals to 0, and this power is also to the power n, so I can directly compare the coefficients, there is no problem. So that's what I will do now. So then if I compare the coefficients, then it will be n plus 2, n plus 1, an plus 2 equals to minus of omega square an. It implies an plus 2 equals to minus omega square n plus 1 times n plus 2 divided by an, times an. Okay, this is the recurrence relation. This is the recurrence relation. Okay. Now let's put n equals to 0. In that case, what we will get? We will get a2 in this recurrence relation. We will get, so if I put n equals to 0, then what we will get? We will get a2 equals to minus omega square divided by 2, or 2 factorial rather, times a0, right? If I put n equals to Okay, let's put n equals to 1. Then what we will get? We will get a3 equals to minus omega square. No, n equals to 1, so this term will be 2 and there it will be 3. So it will be 3 factorial. 3 times 2 times a1. Okay, let's put n equals to 2. In that case, what we will get? We will get what we will get? We will get a4 equals to, so n equals to 2, that means this is a4 equals to minus omega square 4. So it will be 4 plus 2, sorry, n equals to 2, so that means it will be 4 and this will be 3. So 4 times 3, 2. And now if I put this a2, value of a2, then it will be omega to the power 4, 4 factorial a0, because a2 is 2 omega minus omega square by 2 factorial times a0. Similarly, if I put n equals to 3, then it will be a5 equals to minus omega square. So it will be 5 times 4, 5 times 4 a3. And now if I put the value of a3, then it will be, so minus minus plus omega to the power 4, omega to the power 4 divided by 5 factorial times a1. Okay, if I put n equals to 4, then we will get a6 equals to minus omega square by, so here 4 plus 2 is 6 and 4 plus 1 is 5. 6 times 5 times a4, and now a4 I can put from here, so we will get minus omega to the power 6 divided by 6 factorial times a0. Now if I put n equals to 5, I think at this moment you can understand why I am using two different sides, and I am putting the even terms in the left hand side and odd terms in the right hand side. It's because I am getting two different series. This will be in multiplication with a0, and this will be in multiplication with a1. And you can try to guess why we are getting two series, one with a multiplication factor of a0 and another is a multiplication factor of other constant, that is a1. You can try to think about it for some moment, then I will tell the answer. Okay, so for n equals to 5, then it will be a7 equals to minus of omega square. It's 7, so n equals to 5, it's 7 times 6, 7 times 6 times a5 equals to minus omega to the power 6 divided by 7 factorial times a1. So similarly I can go like this. Okay, so what we are getting here is basically two series. Okay, one for this even terms, another for this odd terms. So what we are getting, so we already know that n equals to 0 to infinity a n x to the power n. This was our initial assumption. Okay, but this a n's, what we are getting is for, so let me write it in this way, a0 x to the power 0, or let's not write x to the power 0, just write a0 plus a2 x square plus a4 x to the power 4 plus a5 x to the power 5 plus a6 x to the power 6, sorry, plus a6 x to the power 6 plus dot 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 plus the odd terms a1 x plus a3 x cube plus a4 sorry, what is happening, a5 x to the power 5 plus dot, okay. I can just separate out the even and odd terms. And now what we know is basically a2 is minus omega square by 2 factorial times a0. So every even term we can see there is a multiplication factor of a0. So I can take this a0 common outside. This a0 I can put outside. So then what we have for the first term it is 1 plus a2 is nothing but minus omega square by 2 factorial times a0, but a0 I have put outside. So it will be minus sign minus omega square and there is x square, so it will be omega x whole square times 2 factorial plus a4. What is a4? a4 is omega to the power 4 by 4 factorial times a0. a0 I have put outside. So in that case it will be omega to the power 4 divided by 4 factorial, then omega to the power 4 and there is also x to the power 4. So I can write it as omega x to the power. Similarly, the next term will be minus omega x to the power 6 by 6 factorial plus dot 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 plus for this a1, okay. So the first term is a1, the second term is, so the first term is a1 times x. So we can see that for all the odd term like a1, a3, a5, a7, there is a a1 multiplication factor, okay. Then I can put this a1 outside. Then the first term will be x, right, x. Then the second term will be, so a3 is minus omega square by 3 factorial times a1, so I put a1 outside, so it will be minus omega square divided by 3 factorial times x cube, okay, x cube is already there, plus a5 times x to the power 5. And what is a5? a5 is omega to the power 4 by 5 factorial times a1. So it is omega to the power 4 divided by 5 factorial times a1. I have put a1 outside, so it will be then x to the power 5 minus a7 x to the power 7, plus a7 x to the power 7. So plus a7 x to the power 7, let me write it, plus dot dot, okay. What is a7? a7 is minus omega to the power 6 by 7 factorial. Minus omega to the power 6 by 7 factorial times x to the power 7. a1 I have put outside, plus dot dot dot, continues. Now one thing I will do is, so you can see in this even series of these even terms, here I have put omega x, right. Here I also want to do that, so then I will divide by omega and multiply it with omega here. So it will be omega cube, it will be omega to the power 5, it will be omega to the power 7, like that. So in that case this is omega x and this is omega x whole cube. This is omega to the power 5 x to the power 5, that means omega x whole to the power 5. This will be omega x whole to the power 7 plus Okay, so this is the solution. So y, come on, I made the same mistake again. It's t, it's not x, it's t. Okay, it's t, 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 t. Great. So then our solution will be a0 times 1 minus omega t square by 2 factorial. I'll write the same thing again. Let's not write it. It's the solution. This is the solution. This is the solution. Now, if you can recognize this series, this series, this is nothing but cos of omega t. This is the Maclaurin series of cos of omega t, or rather Taylor series expansion of cos of omega t at t equals to 0. This is nothing but, this series is nothing but sine of omega t. And this a1 and a0, this a0 and a1, a0 and a1, these are two constants. So this yt, this yt is basically some constant times cos of omega t plus some constant times sine of omega t, and this is exactly what we are expecting. Okay, so now I think it is clear that why we chose to do two separate columns, chose to write in two separate columns, one in terms of a0, one in terms of a1, because these are the, as we are solving a second order differential equations, we are expecting two integration constants or two constants basically. So these are the two constants, a0 and a1. And these are the two independent solutions, and it's the general solution. Okay, let's take another simple example and then I will end the class. So though we are doing a power series expansion, it is not obvious or not necessary that we always get a power series. Sometimes we can also get a polynomial. Okay, so let's define something that is a second order Euler equations. What are those? Those are alpha x square y double dash, that means d2y dx2, plus beta x y dash, that is dy dx, plus gamma y equals to 0, where alpha, beta, gamma, these are constants. Okay, this is the second order Euler equation. Okay, so for the question, we will try to solve this kind of equations basically. It's x square y double dash minus 3x y dash plus 3y equals to 0. Okay, Similar, same thing I will do. I will write y as a an x to the power n. You can try to solve it yourself also. Same process. I'll calculate y dash, which is n equals to 1 to infinity n an x to the power n minus 1, right? Because 0th term will be 0, and y double dash will be n equals to 2 to infinity n minus 1 an x to the power n minus 2. So in that case, x times, so what we have is basically x square y double dash, that will be summation of n minus n equals to 2 to infinity n times n minus 1 an x to the power n. So it's because x square times y double dash, okay? This is n minus 2 x to the power n minus 2, and then x square is multiplied with it, then it will be x to the power n. It is minus 3x times y dash, so it will be minus 3, and y dash is this. So if I multiply with x, multiply it with x, then it will be n equals to 1 to infinity n an x to the power n, and then we have 3y, okay, which is plus 3 sum over n equals to 0 to infinity an x to the power n equals to 0. Okay, so I am just writing this differential equation, replacing this y dash and y double dash with this series. Good. What we have is now is basically this series starts from n equals to 2, and this starts from n equals to 1, it starts from n equals to 0, right? So I can write it like that. This will start from n equals to n minus 1 an x to the power n minus 3 Okay, rather than that, what I can do is I can start all the series from n equals to 0. I can write n equals to 0 to infinity n minus 1 an x to the power n minus 3 times n equals to 0 to infinity n x to the power n plus 3 0 to infinity an x to the power n equals to 0. I can always do that, because if I start from n equals to 0, I am just adding 0, basically nothing is changing, because 0th term for this series 0th term and first term is 0. For this series 0th term is 0. So in that case, I can put them together, and what we have is basically n times n minus 1 minus 3n plus 3 times an x to the power n equals to 0, which says the coefficients of x to the power n is a 0. That means n times n minus 1 minus 3 times n minus 1 times an equals to 0. Okay, so either an will be 0 or this term will be 0. Okay, so when this term will be 0, then only for those cases an will survive, an will be non-zero. Otherwise an will always be 0. So only the surviving terms or surviving coefficients will be those for which this term is 0. Okay, it is n minus 1 equals to 0 if an not is equals to 0, implies n minus 1 times n minus 3 equals to 0, implies n equals to 1 comma 3. For n equals to 1 comma 3, so for n equals to 1 comma 3, a not is equals to 0. All other cases an will be 0. Otherwise this solution this equation will not be valid. So what we have is basically y x solution will be a1 x to the power 1 plus a3. So only these two terms will survive. So it will be a1 x plus a3 x cube. So it's a polynomial. Okay, so this is how we have to solve. We can get the series solution of differential equations. So that's all for today. In the next class, what I will do is I will try to formalize when exactly we can find a series solution at all. So there will be ordinary points where we can get a differential solution, and there will be singular points where in certain conditions we can get a series solution, and there are some very specific ways of that. So those are the Frobenius method. So those things will be discussed in later classes. Okay, bye.